And then we start to share our screen. Hold on, this is not the right one. Okay, that's the right one. Need to get back to. Okay, so today we will start with a new topic, a new model. It's called, it's for classification, okay, and it's SVM and kernel SVM, okay. So let's take a very short history. So the complete name is called support vector machine, and it's created said by Vladimir Vapnik in the 60s. But it's pretty much overlooked until 90s. Yeah, for quite a long period of time, AI basically is ignored. Okay, that's because of the what I personally believe is because of the physical machines themselves. Okay, right now because machine got much more powerful. Okay, so that also helps the booming of AI, and the main objective for support vector machine is to find the best splitting boundary, because this is regarding classification. So regarding classification, so if you just imagine, okay, just imagine for what is, it's just you can use something to split the data. So support vector machine is to find the best splitting boundary between data, okay. So here it shows, and that best splitting boundary, so we call it like some hyperplane. So hyperplane. Okay, so that's the goal, to find the best one. So we can take a look, compare these two pictures. For the left one, we have two categories. One is a circle and the other is a rectangle points, And here it shows different, basically over here it's a line, okay, but in three-dimensional, in we call it a hyperplane, okay. You use plane to split the data. And here it shows, you may see, oh, this line looks pretty good, it separates the two classes, but this is just for the training data, for the available data. It's not for unseen samples. Unseen samples, then in this case, suppose, so there may be a lot of chance that a rectangle is here, So in this kind of region, then it will be predicted wrong, So this is not a good plane. But you see, if we take a look at the right side, this diagram, this diagram, if you can find some, we call it hyperplane, optimal hyperplane, And here we also have some key points. So here is the circle points between one class, in one class. This is the rectangle point in another class, And over here we draw this dashed line, and it's parallel to the hyperplanes, And then over here we said between these two lines, we have maximum margin. We can find the maximum margin, okay? And these points, so those points has some, place some K rows, okay, place some K rows. So the goal over here is try to find this plane. And for this hyperplane, then it can maximize the margin. Okay, so how do we find it? So that's called support vector machine. So that's the basic concept behind the support vector machine. Okay, then let's take a look more about support vector machine. So the goal is to find the plane that will provide maximum margin. Is it? And what is the maximum margin? It's the maximum distance between data points of both classes. Okay, so you'll find the data point that basically the most close to both classes, is it to each other? Okay, so those are the points, is it? That's close to the other class, the closest to the other class. We need to find those points. So those points contribute the most, is it? So contribute the most versus points here and the points here, is it? Z contributes the most because they are boundary at boundary, is it? So those data points is that they are closer to the hyperplane and influence the position orientation of the hyperplane. Those points, we call them support vectors. That's how this support vector machine name comes from. Okay, so they are called support vectors. And why we call them vector? Because in math, is it a point? You can represent a point like this. Is it? So this is a vector. Is it? So that's why we call it support. We call them support vectors. And the goal for support vector machine is to maximize the margin of the classifier. Okay, so this is a concept for support vector machine. Okay, we already discussed this. Okay, and then let's take a look at the next slide. So over here, it's the maximum margin intuition. It says you have the decision boundaries, is it, with the larger margins, is it? And then they will tend to have lower generalization error, as it where a model with small margins are more prone to overfitting. Is it? I already explained the concept, is it? So if you take a look like this hyperplane, is it? If you pick this or if you pick this hyperplane, is it? Then the points, is it, fall between that, like in those areas, and it will get predicted wrong. Is it? So overfitting means what? Means fits training data very well. Is it? But not good. New prediction, new data. Is it? So that's called overfitting, is it? But versus, you see, if we use SVM, is it? And if you can find the hyperplane, is it? And this will, so this will handle much better, is it? So you have like, so even though like some points fall between here, is it? So you can still correctly predict that, is it? Even though they are within the margins, is it? But in the other case, if the data fall within the margins, they may get predicted wrong, is it? The chance are much higher. So that's why support vector machine, is it? It's especially good for if you have a lot of data that's going to fall within like this margin area, is it? So then that's, so the samples, the new data fall between the margins, is it? Then it will definitely have advanced feature, is it? So that's the benefits for support vector machine. And how do we derive the weight? Is it because you remember previously when we learned we use gradient descent. Gradient descent concept, is it? So it's to minimize the cost function, is it? To find optimal weight. Is it optimal weight? Because machine learning is a model. You try to use some math model, is it, to represent the tendency of your data, is it the trend of your data, is it all the classification of your data, is it how do we do that, is it so we find either like a sigmoid, so far we learned, is it all linear combination, is it of the weights and so weights. So it's the combination of weights and features, is it? And you combine those together and then try to predict. So that's the general idea. So far we have learned for our model. Therefore, support vector machine, it's similar, okay? But the math behind the support vector machine, how to derive the gradient descent for its cost function, it's much more comprehensive than what we have learned, okay? Logistic regression and add line, is it linear one, and the perceptron, so it's much more comprehensive. But let's just have some very basic idea, okay, about the math background. So over here, it also have the concept regarding positive and negative hyperplanes, okay. And then let's take a look. What does that mean? Let's go back to the previous slide. So if you take a look at these slides, is it? So for this plane, is it? Then we call it, so this class we classify as 1, is it? So it's a positive hyperplane. We call this as positive hyperplane. So all of the data on the right of this hyperplane is they are going to greater or equal than 1, okay, the sigma of this. So that represents sigma. Is it if we write discrete format, because this is vector format. Okay, this is discrete format. Is it? With each of the features, and its corresponding weights. Then in this case, is it? So this plane, we call it a positive hyperplane, okay? And versus for the other class, the plane, is it? Then it's -1. So the combination will be -1. Then it's called negative hyperplane. The decision boundary, this is called decision boundary, it's 0, okay? So this is a concept about positive and negative hyperplane, okay, hyperplane. So you can get these two equations, is it? No doubt about it. And if we use 1 subtract 2, is it? Then you get this expression, as I get this expression. And you get this expression on both sides. You divide the norm of weights, is it? You normalize this with the length of the weights, is it? Then we can come up with this, is it, with this. So our goal is to do what? Is to maximize the margin. Is it because this represents the margin? We try to maximize this. Is it? You maximize this, then you basically try to minimize this. Is it? So the idea is like over here that the objective function of the support vector, is it, support vector machine, then becomes maximize this margin, is it? And maximize that basically because we said it's 2 over the norm of the weights, is it? Norm of the weights. You're going to maximize it. We try to maximize this, okay? So in mass, because weights are unknown, they are unknown, is it? But you maximize, it's not under no condition, is it? So here, it has constraints, is it? The constraint is what? Is the sample needed to be classified correctly. So what's that condition? Written in mass, then it means, okay, if the combination greater than 1, then you predict it's 1. If it's combination less than 1, you predict as -1. So this is the condition. So this is going to be a very comprehensive math problem, is it? You try to maximize this expression, is it, with condition. With these 2 conditions, is it? How do you solve this? So math students knows that, is it? Yeah, and then over here says we can also, you basically can rewrite these constraints as more compactly like this. Okay, like this. And then the goal, because you're going to maximize, so basically you need to minimize the weight, as if we can minimize the weight. It said it can be solved by quadratic programming. Okay, so that's beyond what our class discussion. So on my slides, I provide some math background. Okay, and it involves over here it said Lagrange function. Oh, okay, so it's quite comprehensive. Okay, so if you're interested after class, you can read more information. Okay, so if you're from math, and this won't be a big deal. Okay, but for CS, let's just move on. Okay, so that's anyway. So let's just remember we have the basic concept is you try to minimize the weights. Okay, minimize the weights, and it's the similar thing. Okay, similar thing as what we learned. For the, you remember yesterday we discussed regularization, is it? So here, if you take a look, is it? So this is you try to minimize, but you can also do some penalization, is it? With regularization, is it? So here it also has the C and gamma, okay, C and gamma. Later on, when we learn the models, okay, the SVM models, we will see these 2, we call them hyperparameters. Okay, it's for tuning, performance tuning. Okay, performance tuning. So it's a similar concept to try to penalize, is it? Penalize the goal. Okay, so that's the okay, anyway, so we also learned the logistic regression. The logistic regression is also used for classification, okay? And over here, the key concept for logistic regression is what? Is to maximize the conditional likelihoods. Is it? You remember, the logistic regression, it's not 100% of your predict class it belongs to a certain class. It's the probability of the prediction belongs to a certain class. And the overall the goal is to what? Is to maximize the conditional likelihoods. Is it? And then said that will make it more prone to outliers. Okay. And it's a logistic regression can also be updated. Is it? And it's attractive when working with streaming data. Okay. Support vector machines. Okay, so the one that we learned today for classification, care what? The data points, okay, close to the decision boundary. Okay, so it is very sensitive to the data in this specific region. Okay, so that's the major difference between these two. And yesterday we learned this, is that we read the example. So this is stochastic gradient descent classify. Okay, and it can use different solver. So it will also support SVM. It can also support logistic regression. Okay, so it supports different type based on what type of the solver you want to provide. Okay, so anyway, so here it gives us, and we also know the difference between stochastic versus batch. So you need to have some basic idea about this. Okay, the difference between those two. Okay, support vector machine. Okay, we already have some general idea. Okay, and it says the hyperplane refer also as decision boundary. Okay. Okay, then we can skip that. So we can skip this. And here it also gives a little bit of more comparison between support vector machine and logistic regression. Okay, it's a logistic regression, the threshold for you to decide if a class between certain class is at 0.5. Is it? Then you assign it label either to 1 or 0. Is it? In support vector machine, what we do? The range is between -1 to 1. Is it? That's our margin. Is it? That's our margin. So that's also a difference between those two. Anyway, so we can skip of those, just a math discussion. Okay, math background. Okay, then the next concept. So over here, previously we discussed the SVM. It's linear. So the hyperplane is linear. Is it? We have a linear line or linear plane. Is it to separate? But sometimes, just think about if you have some kind of data, like in circle. Is it? Then how do we use a line or a plane to separate? There is no way. Is it? So then that means the SVM will not work. Is it? The answer is no. Is it? Because we can transform the data. Transform the data and make it still separatable by SVM. Okay, so, but we need to pick some transformation function. Okay, and that transformation function, then we call it some kind of kernel function. So kernel function, basically its functionality is to transform your data, okay, into some other formatting of data. And with that new formatting of data, then it's separable, okay? So this kind of approach apply with SVM, then you can still use SVM to do classification. Then we call it kernel SVM. Kernel SVM. Okay, that's at the very beginning what our class today discussed. Is it SVM and kernel SVM. Okay, so over here, let's take a look. So like in this kind of data, it says you can transform some two-dimensional data set into a new three-dimensional feature space. Is it? Previously, you remember, we also learned, is it a polynomial regression? Is it a regression? It's just you have like the two features. Is it? Then you can add more. Is it? Add quadratic terms. Is it? Add some quadratic. So then we will treat them as features, as new features. Is it? But basically, they are not a feature. Is it? It's just you manually add those high order terms for the polynomial. Is it? Then you remember, sometimes it can improve the performance quite a lot. Is it quite a lot? So here it's, this concept is kind of similar. Is it? Suppose for x1, x2, is it? And then if you do x1 plus x2, is it? Then this is kind of, you create a new feature, is it? So previously your feature space is x1 and x2, is it? So your feature space is 2D. Now you have x, y, x2. We can treat this as x3. This, so then in this case, your feature space expanded, is it, from 2D to 3D? Is it 2D to 3D? Then in this case, a lot of time it may separable your data. Okay, so let's take a look how that works. Okay, with this diagram, that may help you understand a lot, is it? So you have two features, x1 and x2, is it? And if it is a kind of circle looking around, is it? And of course, if you can find this circle, then you can separate them, is it? But with SVM, we don't have circle, is it? What we can have, the hyperplane is linear, is it? But just think about it, is it? If you project the data into three-dimensional, is it, into three? So you have x1 and x2, is it? Here you have x3, is it? x3, x1, x2, is it? x3 is what? Is x1 square plus x2 square, is it? Plus x2 square. Then, did you see? Then you can, this plane, is it? This plane can clearly, is it, separate that? Is it clearly separate? So that's the concept. So this x3 dimension, this new third dimension, is it? And this give us, so this is a previous feature space. Feature space is 2D, is it? Now the feature space is what? Is 3D, is it? With this 3D, then we can come up with this boundary to separate that, is it? To separate that using SVM, is it? So this is a concept, we call it kernel SVM. But the key point is, what is this kernel? How do we find that if you apply that x1 plus x2, then it will make it separable, is it? With SVM, is it? If you can do that transformation, is it? So this is the concept about kernel SVM. And then let's take a look what's the best for kernel Okay. So how do we find the kernel function? Is it kernel function? So using kernel trick to find the separating hyperplane, because it's not just some random transformation, then you will make the third dimension separable. Is it? It's not that case. You need to pick the right transformation. Is it? And after you do the transformation, because this involves huge data. Okay, huge data then it involves big matrix. Is it? Big matrix, and for big matrix, if it does data product calculation, it's going to be quite not efficient. Is it? They said it's very expensive. Is it? So there is a way we call some kind of kernel function. Is it? So that kernel function, so some function regarding two features. So this represents two features. Two feature. Okay. So if you can find some function, is it apply to the feature of the original feature, and then you can make them separable with some same function, is it? And it's the dot product. Basically, you are not going to apply the dot product individually on the feature and then apply it to the kernel. Okay, what you're going to do is that is equivalent to you can do a function on the feature, and then you can come up with some result, is it? And then you apply the function to the other feature, you can have some result, is it? Then you just do the dot product regarding this two. Is it regarding the result of this two files? Is it? So then that saves a lot of work. It's this way it's much more efficient. So the key point is we can find some kernel functions that can achieve this goal. So here it gives us some of the common used kernel trick, okay, kernel function. So one is called, the default one is redial basis function, RBF. When you use sklearn model, you will see this also a lot. And it's also called Gaussian kernel, okay, Gaussian kernel. So basically the kernel looks like this, so that phi is this exponential. Okay, it's the exponential of the two feature. Okay, the two feature, and over the sigma. Okay, over the sigma. So this is one of the kernel function. And then let's take a look some other kernel function also available. You can also use polynomial kernel. Okay, so it lists us, is it here? So this is regarding two feature, is it a two feature? And with the polynomial, and the Gaussian kernel we already discussed. Okay, we already discussed Gaussian, and it has more, and it the next one is called Laplace RBF. Okay, so it looks like this, and we can also use a hyperbolic tangent kernel. Okay, so it's like this. So this is regarding the tangent function. Okay. Okay, so that's regarding the kernel SVM. Okay, so that's the basic concept about SVM and kernel SVM. So next, let's take a look. Share screen. Let's take a look at the example. Where's my example? I need to find example. This one, I believe. Okay, so let's take a look. So we first continue discussion on our iris data. You remember for the flower different category, is it? So to use SVM, support vector machine, is it? sklearn also provides a module, so you can import SVC, it's called. Okay, so you specify SVC. You can specify the kernel. So linear is the one that at the beginning we discussed. Okay. So, and here is that coefficient, is that the regularization C, and by default it's 1.0. Okay, random state, we already did. If you specify as 1, then your experiment is repeatable. So each time when you run, it's going to get the same result. Okay, so we have this SVC, okay, created, then you fit with your data, is it? And be careful, the data is already standardized, okay? You need to scale your data. So be careful when you do any application, okay? Make sure of the data when you do training, they are on the same scale, okay? So this is regarding the model, and here it give us some decision boundary, okay, about the 3 categories. So you can clearly see this is linear, is it? The hyperplane is linear, okay. So here it shows the boundary, is it? Okay, and we can also do predict with the testing data, is it? And find the accuracy, is it? But you remember yesterday we discussed accuracy is not the only one that can measure the performance, because sometimes even though your accuracy score is high, that doesn't mean your model is good, okay? It may be very bad model, okay? So a lot of time you can also use confusion matrix, okay, to do further checking, okay? And over here it shows that stochastic gradient descent, yesterday we discussed, is it? If you take a look, for its loss, is it if you provide a certain solver, is it the loss? If you put as a perceptron, then it serves as a perceptron, okay? If you provide the log for the loss, then it serves as a logistic regression, okay? If you provide a hinge for the loss, then it means it's linear SVM, okay, as SVM. And here it just shows, because all we learned previous, the batch, is it? And this is doing the stochastic, the online, is it? It's the weight adjustment is done 1 by 1, is it? It's not your weight is done via the whole sample, all of the samples, is it? So that's different, because sometimes your machine may not be powerful enough, can handle if you have millions of samples, is it? And each time your weight adjusts, you need to consider all million samples. That's not going to work well. So that's why then in that case, you can borrow the stochastic gradient descent, okay? Okay, anyway, so here it also shows with the stochastic, the online learning, okay, then the SVM, you can do predict, you can find the score, and the PPN, the perceptron, the logistic regression, is there, so nothing new here, okay? And what next to try to show, yeah, for the non-linear separable, okay? Non-linear separable, we learned we can use kernel SVM. Is it? How do we use kernel SVM? Let's take a look. So this is the data. Is it? This is the data. And clearly we can see it's not linear separable. Is it? It's not linear separable. So how do we do that? Is a SVM. Then you still use SVM, but this time did you see the kernel? We use that Gaussian one. Is it? The radial basis function. Is it? The Gaussian one. So this is not the linear one. Is it? So it uses that exponential function, is it, to do the kernel trick, is it? And here you also provide those 2 parameters. So C by default is 1.0, is it? So we increase to 10, is it? And this is a gamma value, okay? This gamma is is for the kernel. When we use a kernel one, it has some parameter. Okay, needed to do the adjustment so that data will work well. And then you can call fit, is it? And then we can draw the decision boundary. Here, let's take a look. Yeah, so this is decision boundary. And we can clearly see that it's not linear. That this is non-linear. So we apply the kernel. Then you see you can still classify that. Is it? Okay, then next let's see the two parameter. Okay, so gamma is it and c is it? So this time we change the gamma and the c is it? We decrease c. Okay, and the gamma previously is 0.1 is it? And with this new set of parameter is it? Then you can see the decision boundary change. Is it? The decision boundary change. Okay, so here. Okay, so here. So the gamma, so what's the gamma's purpose? Is it? So gamma, it says it's provide some cutoff parameter, is it, for the Gaussian sphere? Is it because we use this Gaussian kernel, is it? And if you increase the value, then you increase the fluence, okay, influence of the training samples, okay, which can lead to tighter and bumpier decision boundary. Okay, so that's the point for the gamma, okay, for the gamma. And then let's take a look more of the gammas. Now let's see. So we increase more gamma from 0 point something to 100, is it? And for C, for the regularization, we keep it as 1.0. Then let's see what does the decision boundary look like. Now, if you take a look, did you see the decision boundary? Did you see it's more bumpy? Is it? It's more bumpy. Okay. So this doesn't mean it's better. Is it? So we generally speaking need to find a trade-off. Okay, between the performance, because you also need to consider if it is overfitting. Is it? If it is overfitting in this scenario. Okay. So that's regarding this example. Then let's take a look at the other example. Okay, it's still about support vector machine. Okay, this example I borrow from Andrew Ng. Okay, he is one of the most famous expert in machine learning. Okay. So here we have some data. Is it? It's a pretty straightforward. For this one, you can clearly see it's linear separable. Is it? So it uses the default one. Is it linear? Is it? And then you call fit. Is it on the data? Okay. And we can visually see the result. Is it? So this is the boundary. Okay. And then next, you can also change. Is it? So now we change C. Is it? We increase C's value from 1 to 100. Is it? To 100. Then you can see the linear, that boundary, is it that decision boundary, this decision boundary change. And this decision boundary, you can clearly see it's not as good as the previous one, is it? So this means after you increase C, in this case, it's not working very well, is it? Okay, then next is try to show with kernel SVM, because some of the data is not linear separable, is it? So in regarding this batch of data, is it clearly so you cannot use a linear to separate them, is it? So kernel, we choose Gaussian, is it? The gamma value choose 30, is it? And you can find the decision boundary looks like this, okay? It looks pretty good, is it? And for the third set of data, this is what the data looks like, okay? And what the next part try to show how do we train the gamma, is it, and the C, okay? So what the role they plays, is it? So here it provides a function, is it, regarding the training data, okay? And we are going to pick, so we are going to use different combination of C and gamma. Okay, so here you choose different combination C and gamma, and then you plug them in with the SV support vector machine SVC model. Is it? You will try with different hyperparameter. Is it? Then you do fit, then you do predict, then you can collect the score. Is it? And you will choose the best score one. Is it? The highest accuracy score one. And you will then keep track of the C and the gamma, those two hyperparameter. Is it? The regularization parameter and the gamma parameter, is it? Then this function will return both, is it? So for this case, then we can plug in our data, is it? And this is the value that you are going to train with C and gamma, is it? And then after you run this data set, you will find the best C and gamma, is it? Then you can plug them in for the support vector machine, is it? And then you can fit, is it? You can fit. And did you see? Then you can plot the decision boundary, is it? It's pretty good, is it? So this just shows us another way to find, to tune the parameter, okay? This is to tune the parameter so that you can pick the best C value and the best gamma value, is it? And then when you apply to your model, you just use that, okay? So today, that's the major information